तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, last time we introduced the concept of heterojunction, heterostructure and heterojunction, and today we will continue on that. Few things related to the heterojunction I wanted to just point out. Here is a diagram which has a wide band gap material. See, this is the conduction band, that is the conduction band, and this is the valence band bottom. So, what we did is here showing a diagram, a heterostructure where both are undoped. Okay. So, gallium aluminum arsenide probably undoped. So, conduction band is there, valence band is there, and how much is the band gap depends upon the aluminum content. Okay. It can vary from low value to high value there. So, band gap material. Here we are not specifying what is the material. So, this is the conduction band, this is the valence band. So, you have got actually now undoped layers. So, what you have got is layers going like this, the conduction band, valence band joined with the conduction band, valence band, wide band gap, narrower band gap. You can go on, you can build multi-layer structures with heterojunctions. So, you can see here I have shown there with two wide band gap materials, and of course, here also 1, 2, 3, 4. Okay. You can go on with that thing further. So, what you got is a potential well there, where you can confine the electrons, okay. And the entire energy band diagram now takes a new turn. In fact, I will discuss that in my next lecture. Today, I just point out, usually when you draw a conduction band, what is the meaning? Energy levels are continuous. Now, when you have a quantum, this well like this, potential well, and if this well is narrower this well, then you will not have continuous energy levels, both in the conduction band and valence band. You will have those energy levels quantized, and this will be called as a quantum well. Energy levels are quantum levels, just like the energy levels of an atom are discrete in nature. If I put an electron there, it will have discrete allowed energy levels. Today, I am not going to discuss that, we will come back to that tomorrow, because when we go to next lecture, when we discuss HEMT in some detail. So, that is why you show it here some levels like that. Okay. Some of the levels are shown there with level 1, level 2, level 3. The gaps keep on increasing, like in the energy levels of atom. So, E will have discrete energy levels for an electron. Okay. How it comes up, we will derive and show in our next presentation. I hope you are familiar with the potential well problem. An electron which is in a potential well will take discrete energy levels, and this is a finite well. Okay. So, that part we can discuss, but the main thing to note is there will be discrete energy levels, and if there are more than one electron there will be discrete energy bands. So, you will call them as a sub band, that will bring in later. So, what I am trying to point out here is undoped I have put down there, wideband narrow band gap, and there is no potential change. Okay. All that you will have will be intrinsic level going down like that, coinciding the Fermi level, and you have that a delta E c there. This is only for illustration I have put. Nobody will be having any fun in making heterojunctions with undoped materials. Okay. So, whenever you do, you will have doped materials. In fact, we have discussed that in the last presentation. Discontinuity that you have is because of the difference in the band gaps. Now, this is actually a situation where you have wide band gap material, conduction band, valence band of a wide band gap material. Okay. This is what actually we have discussed last time. A N type material aluminum gallium arsenide joined with the P type gallium arsenide, narrow band gap. This is a band edge, but here you are showing more than one. So, you have got multi-layered semiconductor system, like what we showed for undoped 1, 2, 3, 4. See 1, 2, 3, 4, 5 layers are there. Gallium arsenide, aluminum gallium arsenide, gallium arsenide, aluminum gallium arsenide, gallium arsenide. You will see as we go on after some discussing the HEMT, etc., you will see these have some specific applications. In fact, you can specifically see if I have a structure like this, you can confine your electrons into this portion. We have discussed this last time. This is the delta E c which comes up, and these circles which are shown here, they are the donor impurities. Okay. And these are also donor impurities. They are both N and N. It is not N and P. What we discussed last time was N and P, but N and N, that is a different type of heterostructure. Okay. Isotype, other one is anisotype. So, you can still make heterojunctions with this. Now, even here you will have these electrons, this may be lightly doped, this is more heavily doped. So, electrons from here can be transferred onto this, they will be confined in this well. Now, you notice here I have shown one level here. When there are several electrons, those electrons will be occupying this particular level, and from the uncertainty principle, these electrons cannot occupy same level. Pauli's exclusion principle says no two electrons can occupy same level, but if they are at the same energy, one energy level permitted, they split up into a band. So, this will be a subband. Similarly, we will have a subband here. I have shown more than one here, there may be one subband here. So, in such a situation, what would happen would be, supposing I have electrons confined here and they are occupying here, and if I have a level here, there are no electrons here. If the electrons are here, let me just show one level here. If the electrons are here, they can make a transition from there to there, emitting light corresponding to this particular wavelength. If you recall, this is gallium arsenide. I am just showing the undoped situation, which holds good for the doped also. This is 1.43 electron volts. The wavelength corresponding to that is something like 0.87 angstroms. 1.24 divided by 1.43, that is the wavelength in microns. So, it is about 0.87 microns. Now, there are no electrons here in this case. When you confine them in a well like this, so these electrons are above that band gauge, that is the allowed level. Now, if you allow that to make a transition, that is when they recombine, they will get transferred from this level to that level, and the gap is more. So, if the gap is more, what have you achieved? What you achieved is the light emitted from here to here actually has a wavelength less than that, corresponding to this wavelength, because energy is more, wavelength is smaller. That means you are pushing towards the visible range. So, you can get light of different wavelength by making combinations of these things. In fact, this is one of the structures people think of quantum lasers. Confine the electrons here, populate them as much as you want, allow them to recombine. I hope I will have some occasion to discuss towards the end some things about these things. So, you can have multiple multi-quantum level structures, multi-layered structures, with which you can have an effective band gap, not this, but something in between. So, that sort of thing can be there. In fact, there is one level and another level, electrons will be occupying the lowest level, like in another case. So, it will be band. If you increase the concentration, maybe it will go to the next level. Okay. So, these are some of the tricks one can play with this type of structures, heterojunctions. So, you can see the compound semiconductors gives you the facility not merely to adjust your band gap by changing the material composition, gallium arsenide GaAs gas to L gas. By changing X you can change the band gap, plus multiple layers you put alternately, it gives another dimension altogether. So, for optoelectronics applications, that is another thing. But here what we are talking of is the transistor, you do not need multiple layers. But I just show one more diagram. So, this is NN uniformly doped, doping here is the same as here. Okay. Still there will be transfer electrons from here to here. Now, you have another situation that is called modulation doped. Okay. This in fact, you will the transistor that is made out of this is called MODFET, modulation doped field effect transistor. That is also called, it will come later, that is also called high electron mobility transistor. So, now here this is the structure that we saw. I showed you this is p type, but in the extreme it is undoped, okay. But you never get undoped, it will be lightly doped p. So, when you have that, you have got the electrons here and you have got this diagram and the electrons are confined here. Okay. Now, if you remove those things, instead of multi layers, you go on to 2 layers. That is what we discussed last time. Okay. I hope this is clear enough. This is just I showed undoped, all the layers uniformly doped, N type, and next one alternate layers doped, that is selectively doping this portion. These are will be layers arranged one over the other. On the top of bottommost layer will be that, you can go on to the top. Okay. So, the energy band diagram is drawn horizontally, but layers are one over the other one. Okay. So, you grow layer after layer, one layer you dope, other next layer change out aluminum gallium arsenide, dope it. First layer you do not dope with gallium arsenide, dope this layer, do not dope it, dope it. It is very easy to do in technology in MBE. That is, as you finish that gallium arsenide layer, switch out aluminum gallium arsenide, letting in aluminum. Okay. If you are doing MOCVD also, you just switch on trimethyl aluminum, you get aluminum gallium arsenide, and you want to dope it, add sulfur bearing compounds, sulfur monochloride or hydrogen sulfide, you add on to that. So, then you get that layer doped. Now, how thick that layer you want, that is decided by where you want the energy for a multi-layer structure. But in this particular case, where you have only 2 layers, all that you are looking for is this notch, which is created by this. In fact, we have shown last time how to generate this energy band diagram for aluminum gallium arsenide layer. When you have multi-layer structure, just let me go back once. Same thing holds good. You can see there is a notch here from this side also there is a notch. So, the confinement takes over the entire layer, whereas here the confinement is here only, because this is a thick layer compared to this. Now, what we said last time is you have this notch delta EC or discontinuity in the conduction band is given by chi 2 minus chi 1. We have derived that. That is called Anderson's model, the first model to understand. And delta V will be equal to whatever delta E g is there minus delta E c, or delta E v plus delta E c is the delta E g. Okay. I think that is clear enough. See, I have that is the conduction band. You do not have to draw the vacuum level now. And then parallel to that, up here up there, discontinuity there. I am not explaining how we went about that, because we spent quite a bit of time explaining that. That is the one. Now, you will have a Fermi level there. Okay. N type close to intrinsic, P type. Fermi level can be there. In fact, it will be there, because below the Fermi level electrons will be occupied. Electrons will be there below the Fermi level. This notch will hold the electrons. Okay. Now, what I am trying to point out is this is delta E c, and this is delta E v. Sorry, redrawing it here so that it becomes clearer to you. And this I am sorry, yeah, this is the valence band edge, this is the conduction band, that is E g 1 and this E g 2. So, difference between the two is sum of these two, and sum of these two is this plus this is delta E v plus delta E c, that is the difference in the band gap. Just visualizing it, because there are too many diagrams lines there, this is only diagram. For further discussion, we do not need that, you can drop this and draw only conduction band. So, whatever is happening here. So, you will see, to start with we had the 3 levels put there, 0 level, conduction band, valence band. Now, here I removed that top level, later on we will remove all this also, because whatever is happening is here. So, delta E c plus delta E v is the difference between the band gaps. One of them if you know, or two of them if you know the other one. Now, in fact, they have measured some of these quantities and arrived at a conclusion that delta E c by delta E g is 0.6 to 0.64. Okay. And now, few things I want to just bring out, because we have drawn certain diagrams in a certain way. So, we will take a look at those diagrams and also see this. Here delta E g, now we are talking of all gas system. Okay. Now, delta E g is the difference in the band gap. Now, how much is delta E g depends upon x, that x. Just let me go to the forward ones and take a look at that diagram. I deliberately put this diagram because we have been drawing all straight lines. That is idealistic. It tell you that it is almost linear. It is not linear, it is almost linear. So, if you see this portion is fairly linear, but here it is not linear. I have shown 3 curves now. All through we have been drawing 2 curves. I am putting this deliberately because you will see this sort of diagrams. But whatever we have been telling earlier holds good in this case also. Now, I will just put those things. We will go back to those explanations, experimental results later. Take a look at this diagram. Okay. See, what is happening is you have gallium arsenide and this diagram needs some attention. That is why I am just going into that. This is the 0 level, K momentum versus energy. Now, usually we used to draw only one diagram. I used to draw one diagram here like this, but actually it goes like that, continuous. Okay, and this particular quantity is 0.35. Okay. Draw that diagram here. This is the if I take the 0, this is called as the x or tau. This is called the just some notation to show that this is a direct band gap portion tau. Let us not worry much about that symbol, that is direct band gap location. Okay. So, you can see the diagram, that is 1.43. Okay. That is 1.43, and this quantity here is actually how much? About 1.78. that quantity. See, people quote numbers which are 0.35, 0.31 in that range. So, it is around that. So, now you will have also one more level which actually goes bit higher than that. Okay. It is bit higher than that, and that particular thing I have not shown. This is on the, this is along the 1 1 1 direction, and this is along the 1 0 0 direction. In the crystal, if you move in the 1 1 1 direction, 1 1 0 direction, you get these values. If you recall, there are more than one values like that. I am just showing in the 2 dimension just 2 the values here. Okay. This is just whatever I have borrowed from the physics, I am just putting it across. Okay. So, this particular energy, okay, that is something like 1.9 or so, 1.9 close to that. Okay. See, we were drawing some effective thing earlier with the linear thing. So, now this is actually the, this is called the x. Just 1 minute. If you put, see the diagram here, this is the direct band gap, this is at 1.7 something, okay, and this is about 1.9 or so. So, this particular x, this is x, this is called L. So, this is actually x and this is L. Just show the boundary of, it is called a Brillouin zone actually, let me not say that, because the boundary of that region where we are plotting this, that is L, this is x. There are 2 values near that portion. If you take aluminum arsenide also, you have similar structures. In aluminum arsenide, corresponding to the center, that is indirect band gap actually. Okay. So, you can see the tau, I will now come back to this. So, if you see here, this is the tau correspond direct band gap, and there is a direct band gap corresponding to this level here, that one line going like that. It is not really straight, in fact, it will try to be straight, it latches on to the direct band gap, and if you vary x, that direct band gap keeps on varying from 1.43 to 3.02, this is about 3.02, that is what we have been telling. Earlier we were plotting this straight, strictly it is not so, it is not a perfect straight line, there is a slight curvature here. Now, there are other lines which are coming up, that is this x line. X line is actually along that 1 0 0 direction. Okay. So, if you see x line, this is something like 1.9 or so, close to that. Okay. This is where you will see the band gap. You know, sometimes you will see literature, one is 0.35, other one is something 0.5 or something like that, but this is the one which is closer. When you look at the transition from here to here, you worry about that. But in this case, aluminum arsenide also, you will have direct, which is 3.2, and the one along the 1 0 0 direction, if you vary x, this x, that is this x, if you vary along the 1 0 0 direction, that band gap will vary from 1.9 to 2.17, this 2.17. So, we were looking at actually 2.17 only, and we are looking at this somewhere here, join them together. So, this band gap, let me go to this band gap ties along with okay, you have the aluminum gallium arsenide, okay, that is gallium arsenide. Now, here corresponding to that, that is draw it slightly bigger, so that I can accommodate the whole thing. So, you will have that one is about 3.02 or so, slightly more than 3 electron volts. X so, if I vary this mole fraction, this will vary from 1.43, from 1.43, it will keep on varying to that. That is the meaning of that line tau that we have drawn there. Okay. Now, similarly, you will have along this 111 direction, that is L direction, you will have a band gap which is actually equal to, is also indirect, but is about 2.23, something like that. Okay. That is actually L, that is 111 direction. So, this will tie down to that. So, whatever I have marked L corresponding to this gap, that will vary from 1.78 to 2.2. Plot is a straight line, it is not really straight line, it is slightly curved, it will go into that. There is one more along this 100 direction, that is 100 direction, and this is 111. Along this we have got one more, which is actually even smaller than that. That is actually equal to 2.17. So, what we are telling is there are three things which are tracking. One is this direct band gap 1.43 tracking with that 3.02, keeping on increasing almost linearly, but not exactly linearly. Other one is 1.78 tracking with the 2.23, close to linearity, but not exactly linear. 1.9 tracking with the 2.17. So, that is why x tracking with x, L tracking with that L, tau changing with, that is k equals 0 tracking with k equals 0, which we are telling is you can now have as many number of semiconductors as you want with initially direct and finally becoming indirect of that band gap. As x varied from 0 to 1, and we have done this earlier, but we are with bit more rigor we are doing that, because you will see this sort of diagrams in literature. But ultimately what boils down to is whatever we have been telling, but the values may be slightly different. So, you can see now that direct band gap portion 1.43 tying with 3.02 all the way in this diagram tau, and that x varying from 1.9 on the left hand side there to 2. I am sorry, x varying from, let me just 1.9 to 2.2, that is also indirect band gap. Then you have got the other one, that is L varying from 1.78 to about 2.23 or so. Now, what is actually the band gap depends upon the minimum. Here 1.43 minimum, here 2.17 is the minimum. So, the effective band gap will be varying from this along this path, the minimum of all of three. Now, you can see up to this point it is direct band gap, that is the tau is the direct, minimum is the tau, and beyond that, that is something slightly more than beyond 0.1, 0.4 x equal, that is mole fraction about 0.4, 0.45, beyond that is indirect band gap. So, you can generate direct band gap material or indirect band gap material. Why I put this diagram to you is to get further clarity about this particular diagram. Also, when you take 0.4, that is there, about 0.4, you get about 1.93 or so in that range, somewhere here. So, from this diagram, if you just draw straight lines, you will not get that 1.93. Okay. In fact, I put earlier when I drew straight line exactly, I put 0.3 corresponding to that, but it is a very crude approximation. The real thing is that. In fact, if you see the indium gallium arsenide, as x is varied, it will not be really straight. So, the band gap that you really get are slightly different. Where x equal to 0.47 gallium concentration, you get 0.75 electron volts band gap because of its nonlinearity. So, now what we are telling is when x equal to 0.4, let us go back to that now. Let me remove all this now, because we understand these are the diagrams. These only represent the range directions along the crystal. Okay. Let me remove this. So, what we are trying to tell is x equal to, that is the mole fraction aluminum mole fraction x. So, when x is equal to 0.4, you get actually E g equal to 1.93, around that. Okay. E g 2, this is L gas. Okay. Then E g 2 for gallium arsenide, you can call E g 2 is given whichever way, is equal to 1.43. So, delta E g is 0.5. E g 1 so, what we have, I will go back to that previous slide where that is put. Delta E g is 0.5 electron volts at x equal to 0.4. In fact, to get that, I put that diagram for you, because if you just put straight from 1.8 to that diagram, you won't get that. Okay. Now, what people have observed is, this needs some little bit of explanation. A qualitative understanding we will try to get. Delta E c equal to 0.64 times delta E g. That is, delta E, this particular delta E c, what you get here is 0.32. Okay. This is actually a measured quantity. They get from optical measurement, they have seen that the delta E c, the discontinuity in the conduction band is about 0.32 for the x is equal to 0.4. Around that 0.32, 0.3, there also will be some errors in measurement, but it is almost this one. That is why I put that approximation there, because people have put here 0.62 to 0.64. I am putting an argument now to understand this. Okay, we will see how, watch me carefully. So, delta E c is this. Okay. Now, the values, this value is different from the chi 2 minus chi 1. Chi 2 minus chi 1 is quite different from this. Okay. Now, also they have seen delta E v is obeys the formula 0.47 times x of aluminum. So, x is 0.4, you get 0.18. So, 0.18 plus 0.32, 0.18 plus 0.32, 0.5, which is that. So, now let us see what is the trick here. Okay. So, the whole thing is, you write, actually we use this equation, particularly it is valid for L gas system. You cannot say 0.6 times, that is this formula 0.64 times delta H will hold good to all the systems. It is like telling the neutral level in gallium arsenide is 1/3 of E g. In silicon is 1/3 E g above valence band. But if you take indium phosphide, there is a different story altogether. Neutral level is not at 1/3 E g above the valence band. So, like that, this particular term will be different for different systems, therefore, L gas system. Okay. Now, how does it come about? What is it that is hidden in this? The discontinuity delta E c, okay, and the band bending, they are tied together. They take place finally, so that the neutral levels are aligned. See, like in the case of metal semiconductor Schottky barrier are there with a neutral level. Aluminum gallium arsenide and gallium arsenide belong to the same, almost the same species, because after all aluminum can replace gallium very quietly to give aluminum gallium arsenide. So, the neutral level in gallium arsenide is at 1/3 Eg above valence band. So, what this tells us is this forces the neutral level E naught on either side of the junction to align, and what is the whatever I have put there, let us see. I will go through this explanation. Okay. This is what you can see. The energy band diagram, let me draw first. In fact, the conduction band is sufficient, but since we are discussing the other aspect, we will draw the valence band also. Okay. Formula level there. What we are telling is this band, this delta EC and this band bending will of course has to do this Fermi level aligning. When that happens, apart from the Fermi level aligning, the potential and the delta EC together are such that what we are telling is they such that neutral this particular level E naught neutral level. Just watch very carefully, because I am just giving the theory which has been arrived at after number of publications. The moment it was not matching, everyone just plunged into that and said, here is my explanation. Ultimately, what is now accepted is this discontinuity and the potential, everything will adjust such that the neutral level actually of this neutral level and the neutral level of that tend to align. If they are exact, that is the best, but they may not be exact, but it will be close to each other. What happens if they are not exactly equal? Now, the Fermi level is here. See, if they are exactly equal, this is actually the interface common to both. This is outside the band gap of this gallium arsenide. It does not see that really. It sees maybe in terms of this potential distribution. So, here all these levels are occupied, because Fermi level is above that. All these levels are occupied, all these levels also are occupied. I am taking a situation where the neutral levels are perfectly aligned. Okay. So, what is the situation if they are perfectly aligned? Charge on this aluminum gallium arsenide at the interface is given by what is this gap? Their acceptors, okay, DIT multiplied by that energy gap, and all these acceptors are above the neutral level and they are below the Fermi level. That means they are occupied. When they are occupied, they are negatively charged. They are not neutral. Below the neutral level, they are donors. They are occupied. They are neutral. So, that is perfect. I hope you are able to understand that. Acceptor level occupied is negative. See, I always have suspicion whether people follow. Donor level, it is occupied is neutral. Donor level unoccupied is positive. Okay. Acceptor level unoccupied is neutral. That is, the hole is present there. That is plus. That is unoccupied. Unoccupied by electrons. But when it is occupied by electron, that hole is gone to valence band. That is negatively charged. When we say occupied, unoccupied, we say occupied with electron or not. When it is occupied electron means the hole which was occupying that has left the place. That means an electron has gone there, negatively charged. So, that is why an occupied acceptor level is negatively charged. All of them are negatively charged. Perfect harmony between the two layers, in the sense the charge is present here which belongs to both of them common. supposing there is a mismatch, okay, what will be the constant? You do not have to worry about that, because that is not coming on to this particular interface, the gap, energy gap, it is outside the band gap. So, it is not interfering this. So, what is common here? Now, suppose the levels are slightly different. Okay. Let me draw that diagram now. So, here it is perfectly neutral. Let me take a situation where the neutral levels are exactly aligned. Charge on both sides in the interface is same. There is no charge transfer taking place there. There is no dipole layer formed. Whereas, if I have this is the neutral levels are exactly aligned or have exactly aligned here. Let us take the situation where I am trying just another diagram to show that. I am deliberately drawing this like this, just to show the two levels. I will draw that, and this one also slightly here, corresponding to gallium arsenide. So, neutral level of this one is here, okay, and the neutral level of that one is there. Let me draw a bit magnified so that you can see it. I draw two lines here. There is a single line, but I have drawn two to distinguish. This is here, that is there. What is the situation now? More number of electrons here on the gallium arsenide, less number of electrons here. So, but they have to be just live together. So, what happens is there is a charge sharing takes place, electrons from here to here move, okay, and this gets negative charge, this gets positive charge. A dipole layer is formed. Okay. In fact, the theory what it formulated says that it is not a condition for minimum energy, it must be minimum. Okay. But even if you do not agree with that particular situation, ultimately charge transfer will take place and this will become equal as close as possible. So, this is not a favored situation where neutral levels are same, it is a favored situation, because in this situation the charge transfer will take place further, so that they are moving closer together. So, they may not move exactly, but it will move close to each other. Like in the case of Schottky barrier, the Fermi level moves closer and closer to the neutral level, it is not exactly matching. So, that charge there is minimized, charge at the interface is minimized, it moves up to that point. Charge there is balanced by the potential hill. Here of course, other criterion also comes into picture. So, the charge in the interface, the discharge difference between this and that should be minimized. That is all simple thing we have to say. So, here it is charge between difference between the two is 0. It may not be exactly 0, but close to that. That is all what is said in the statement here. So, the discontinuity in the band takes place such that the charge at the interface on either side is minimum. In the sense, charge difference is minimum, or net charge on either side. Okay. If there is a charge difference, one becomes plus, one becomes minus, that is minimized. So, aligned each other. This is what you have said here, just as a statement, but ultimately what happens is each one of them force the level to align to each other. If the line up does not occur, charge transfer takes place between the states, okay, on either side of the interface, and this will create a dipole field. From the energy considerations, the system favors dipole minimization and therefore equalization of E naught levels. That is as a statement I have put there. Now, if you agree on that, okay, now we know how to work out the number. How much is this delta EC, we can work out from there. So, the entire criterion is the alignment of the neutral level, so that charge difference on this side and that side are same, 0, charge on both sides are same. If there is a difference, there will be charge transfer to bring them closer to each other. So, it may not exactly match, but close to each other. Now, let us see what will be the situation. Okay. What is this quantity now? How much is delta E is our question. How much is this quantity? Let us put that. Let me put this as E naught and this as, let me remove all these things now. Put this as E C 1, conduction band 1 and E naught, and this is E V 1. E naught by E minus E V 1 is actually equal to 1/3 E g, and E C 1 minus E naught is actually equal to 2/3 E g 1. Okay. So, this is E g 1. I hope I have marked it as E g 1 and E g 2, does not matter. With reference to this diagram, this is E g 2 band gap. This is that. Okay. And this quantity E C 1 minus E approximately equal to 2/3 of E g 1. And this is E C 2, and this is of course also E V 2. See, E C 1 is there, E C 2 is there. So, E C 2 minus E naught is equal to 2/3 of E g 2. This workout of course is not mentioned in publications somehow, but it is mentioned that the neutral levels tend to align, then you can work out this. So, if you know the neutral, so okay, delta E c is equal to is equal to E c 1 minus E c 2, that is actually equal to 2/3 of E g 1 minus E g 2, which is 0.66 times delta E g. Okay. So, that is actually equal to, let me just put this here once again, just a bit closer, delta E c equals E c 2 or E c 1 minus E c 2, okay, which is actually equal to 2/3 of E g 1 minus E g 2, actually equal to 2/3 of delta E g. Now, what they have seen in experiments is, you can go back and see, almost 0.6 to 0.64. So, that depends how much alignment is there between the E naught levels. If it is exactly aligned with that 2/3 E g, then you will get 0.66 times. It is slightly different from that. That means it is not exactly aligning, it is not possible. There will be some charge transfer that has to take place, because after all it is governed by this. Let us just take further look into this thing. Now, I just want to take a look at this particular distribution of, I will try to discuss few things now related to this diagram. This is actually the n plus aluminum gallium arsenide heterojunction with undoped gallium arsenide, doping concentration unintentionally doped, and depletion layer here, because charge transfer has taken, entire band bending has taken place. All this has taken place because this layer is depleted. This is depleted, okay, and you have got this charge transfer taken place onto that side. And this is depleted, so it is bending down. This is depleted, so it is bending up. So, that is the thing that we have discussed. Now, what I am trying to point out is, compared to the homojunction, if you had gallium arsenide and have been the potential there, distribution. Let us draw that. Let me draw a fresh diagram, because that what we have drawn there, what you see in the slide is slightly the final diagram I have drawn. Let us take a look at that. So, if it is a homojunction, gallium arsenide, gallium arsenide, what would have been there? This is N plus, this is P, lightly doped. Okay. If I have that, what would have been the energy band diagram? N plus P, P minus, lightly doped. What would have been the diagram? I would have got the depletion a similar value. You get a depletion layer here. What is the barrier here that ultimately obtained? That is the built-in potential. And you have got here, you can draw the same diagram that you have been drawing for the Schottky barrier, energy distribution of electrons. And here, energy distribution of electrons, minorities, till they match the difference has taken place. Okay. Now, if you take a look at the, if you replace this gallium arsenide, what happens? There is a notch here, okay, and I just draw this, maybe I will continue on this next lecture, but just now, if it is aluminum gallium arsenide, okay, this is for gallium arsenide. I am drawing the conduction band the same way, let us not worry about that. What happens is here it comes down like this. Then if it were the same built-in potential, how it would have gone? Like that. What happens if it is the same distribution? Same potential barrier as gallium arsenide. Then this is at a higher level, thermal equilibrium, this is at a lower level, the whole thing is pushed down. Then more transfer of electrons from the aluminum gallium arsenide to gallium arsenide. If more transfer takes place, what happens to this? That will come there like that. So, in the case of single crystal, you get homojunction. If you get that potential barrier, you get more potential barrier. I will discuss again some details about this in the next lecture, because I do not want to hurry it up. So, what I am telling is there is additional potential drop here corresponding to delta E c. That means there are additional electrons than the homojunction here. How much electrons are there depends upon how much is delta E c is. So, delta E c, the whole thing which resides the notch, it is the one which decides how many electrons are there. I will take this up again in the next lecture, but this is the point that you should note. This is for, I have just drawn only that portion, let us remove that, because that thing will go down. Thus, this is for L gas, gallium arsenide system. Okay. With that I stop today.